Tomorrow, and so I'm just watching it from Japanese scratch, something I've written, and so it might, in Japanese might come up. So at least you can
Three of us
find
can
something.
understand. Or maybe four of us. Raphael can understand from
My
Japanese.
interest
No,
is
Japanese.
to find the mechanism possibility of possible mechanism of the chiral crystal growth. And there are many chiral crystals which chiral molecules coagulate or form chiral crystals like forms and so on. And first, I want to first summarize the experimental facts. Probably you know, but I want to be sure. Keeping in Pope first, the growth of Venice O3, crystal growth of Venice, and when it is still and the solution is evaporated, then you get 50% of this of the D type and the L type. And if you add these both, I don't know whether it is correct statement or not. It was written first in Japanese, and I have to translate it into English. I don't know. In English, do something, and then you get 70% of L, and that was written in both. Keeping on both paper. If you add some seed, that means if you have some crystal and then crush it and then serve it, and then many crystals are formed with the same hierarchy, and this is just the secondary nucleation. And the nucleation produces the homochiral crystals. And 50% means this kind of step up. This is the number of experiments, and this is the ratio of D type, and the probability is just 50%. And the next experiment is conducted by Dupuy and his group. He prepared the solution and then stir it. Then he obtained C type or L type with this 100% of homochiral crystal. So the interpretation was that the single mother was nucleated, and it was by the stirring broken into small fragments, and secondary nucleation take place.
Yes, tomorrow McBride will be here, and the person who elaborated this mechanism was McBride. Professor McBride was the person who published the paper about this secondary nucleation process, the mechanism, in undergraduate to me on this record.
Is correct.
Tomorrow he will be here, but he published that in the literature, and people generally ignore the paper because this was in a chemical journal.
Sorry.
Okay.
Me too. I don't know. I know.
Okay. He will be here tomorrow.
Okay. So far, up to here, I understand the secondary nucleation mechanism. But Wiedemann has done an experiment in 2004, and he has solution, and also he added D type and L type together as crystals, and then glass piece. I don't know whether it is correct. In English, glass balls, 4 or 6 rather large glass balls, and then stir it and to crush and abrasion of crystals by glass bead, and that provides the recycling process, and then we got the homochiral crystal. This is the way we find the degree of homochirality develops as a function of time. If there is some priority to D-type is, for example, is a little bit varying, then the whole system comes into D-type. If it is L, then O-type.
So what is the black and what is the gray?
Black money is E-type, I think, and gray one is L-type. So a little bit of superiority of.
And this is versus time of grinding.
This is versus time of. So 8 hours.
Okay, and this is the
Reconcentrations.
Actually, okay.
So after 8 hours, every crystal turns out to be a D-type. If D-type is preferred initially. If L-type is preferred initially, then everything turns out to be L-type.
And the excess has been added artificially in this case.
Yes, from the beginning.
From the beginning you have added L, or you get some other excess of D,
yes.
And then you start grinding the system,
yeah.
And then what you observe.
Yeah. In fact, initially there was no the solution. There is only solution. Solution means solvent. No solvent is solvent. Only solvent. And you add D crystal and L crystal. Then it dissolves. But the amount of this solution is the amount is rather higher than the super saturation. So there is some remnant of D and L crystals. And the
sodium chloride doesn't have any chirality, multi-chirality. After dissolving those molecules, some crystals, D crystals and L crystals are remaining in the solution.
So the solution is not complete.
Solution is super saturation. Saturated solution. Saturated solution with D crystal and L crystal.
Okay. So when Vidima comes, he will explain. So I already understand it by some point of the crystal growth. So the most general might be you have a chiral monomer and that builds up to dimer, chiral dimer, trimer, and at a certain point it may form chiral cluster or chiral embryos, and then goes on. That's the most general way. Not most, but it's one typical way of adding monomers in the growth process. And this can be analyzed, but I wanted to search the minimal model, so I simply assume that diamond has a regulated chirality because to make the model simpler. And critical size for the nucleation of the crystal is also diamond. That means only if diamond breaks and decomposes back to monomers. And further on, trimers and higher polymers or higher clusters cannot. It makes life easier. So this is a growth process, but I want to introduce somehow the recycling process.
But this assumption
Yeah.
that the primer cannot decompose because the primer is below the critical size. And if it's below the critical size, it decomposes. I mean, any cluster which is below the critical size should decompose.
Yes. So therefore, I assume dimer is already a critical size. Trimer will not decompose.
So you think that the crystal can be formed of the dimer?
Yes.
You don't need to worry about critical sizes of this. You don't need to worry about critical sizes, it's not important.
I mean, he's trying to do a minimal model, right?
It's
not a realistic model, it's a minimal model.
That's real diamond.
The question is, if you speak in terms of crystallization, crystal nucleation, in order to form a crystal, you have to cross the critical size. Now, we know from the studies that you have done that you need at least 150 molecules in order to cross the critical size.
in the solution.
And dimer, you cannot, dimer is not, you cannot cross the critical
Yeah, but
size.
then, I mean, he would call it somehow a conglomerate, which he calls R2, right? Something like this?
Just as like this R is a conglomerate of 50 molecules.
Yes.
The critical size, the critical changes in aggregation rate with size just means some clusters are less likely to be seen than other cluster sizes. You still have
I
a
want to be
structure.
more appropriate later, but first I want it to be
The mechanism.
the simplest.
Mathematically equivalent. It's not chemically equivalent.
No, the question is again,
Crystal size is just
I mean, it's-
the mechanism is to operate whether the crystal size is there or not.
very simple, that primer and iron do not decompose. The question is, I think that primer and iron, primer definitely should be in a equilibrium with monomers.
Sure.
with
I know
carbon.
that. But just assume to make the life simpler. If it is essential, then the model fails.
I mean, if he does a real thing, nobody would know if he's going to cheat us or not. Right? Because then it's so complicated, nobody can
This is
identify.
actually, I think this is exactly the point of this meeting. I mean, yesterday night I was always thinking about the anti-numeric cross inhibition mechanism statement, and I will speak about this. I can tell you something that I think that. Now, the problem is we're coming to different cultures. Different cultures have somehow to find a common denominator.
May I?
Yes, please continue.
So far for the crystal growth part, the simplification for the growth part, and I somehow have to introduce a phrasing by style. And that first, the simplest case, I just broke the tetramer into two diamonds. And then up to the, so that means these crystals cannot go more than tetramers. Pentamer or
Pentamer, yeah.
hexamer will not exist in this world, this model world. And then I can construct the rate equation, and then rate equation for the monomer, dimer, and trimer, tetramer, and that's sufficient, and that's all. And then we use it to reduce iron.
Another question also, again speaking from the mechanism of crystal nucleation and crystallization, we have evidence that a nucleus can grow in a supersaturated solution by combination of clusters. And we have tetramers and pentamers, they can combine. And when they combine, some of them can form a decamer, or larger clusters, which help them to try to cross the critical size.
That's a very, very good information for me, because you may see that those cluster, in fact, a dimer, that I will come later. So in any case, here I have only monomer process, and then what I have got is that these abrasion brings the system to catalytic process, but it is only autocatalytic, and so you cannot obtain the chiral, you cannot break the chiral seeds up to for this model. You simply can write the equations for dimers, trimers, tetramers, rate equation for that, and then find the fixed point. In the long time limit, system will come to the end, and what will be the because it is a closed system, so monomer is decreasing, and here you are feeding the dimers. But at the last, it comes to the steady state, and then you can find what kind of steady state is possible, and that is the symmetric state. So up to here, with only monomer incorporation, we cannot you cannot break the chiral symmetry. So I have to go to hexamer and to break the hexamer to 3 dimers. But that's with this process, it is only with this process it is also not possible to break the symmetry. What I really need is this dimer forming 2 dimers form tetra, and this breaks the chiral symmetry. So, as you have said, if in the solution dimers or higher polymers coagulate and form crystal, then this kind of chiral symmetry breaking is possible. But as a physicist, and I don't know whether, and in the usual textbook, one only sees that the monomer incorporation for the crystal growth. So I just have wondered whether it is
more the case. I think that more and more examples are drawn, and you can see that the crossing of the critical size, the probability to cross the critical size, is done by combination of clusters, and there are evidences there are such clusters in solution, many by several methods, and this is what is really commonly accepted today.
Okay, if that is the case, then I'm very safe. I feel very, very safe. That these so chiral units combine to form chiral larger cluster or crystal, and that is the origin of the chiral symmetry.
There is also another point here. There is also another point here, that if you assume this mechanism, the clusters can combine with one another, in systems like achiral, composed from achiral molecules like sodium chloride, the moment that you have a collision between an R cluster, large cluster, and a small cluster of S, they combine, and then you can get a larger cluster R. Because the sodium chloride is achiral, as they combine, as they collide, okay, you can convert some of the S clusters into large R clusters. So the large one always wins. And I think this effect should also affect your mechanism. This will help you.
That will help more.
Yeah.
But I wanted to find out the minimal part. So mainly this is main thing I have done. The other thing is that to make the thing more complex, you can go to a higher mass. I don't know how to say it. So from here on, I have no time to change from Japanese to English. So you just go not only to dimer, trimer, larger size, and do some kind of Monte Carlo simulations. And without C, this is the E at that time. This is for short time, E up to something 1, and this is about 1200. Without any speed, you just go from here. It's just fluctuating because of the Monte Carlo process. If you add, there are 10 to the 5th achiral molecules, so to say, the substrate. And if you add the chiral L1, L or P clusters of the size 10, 100 of them, or thousands of them, or 3,000 of them, then it will increase the nationality excess. And so this is the secondary nucleation, in fact. As a function of time, how the size distribution varies. This is not the size distribution itself, but the difference of the L and P. And for example, first you add 100 of size 50s of L, then after time P equals 20. The added size is here, but it goes up here. So L is this is the original added one, and this is the spontaneously growing crystal, small clusters, and they can be L or P, so they are clusters. But the initially added P L clusters grows up to 100, 200, 600, and 1,000, and finally they soak up every small clusters because it's getting too large, and so the Oswald writing takes place, and the larger cluster eats up the smaller ones. So finally the larger one, or the initially added type dominates. So complete homochirality is accomplished. So with the monomer addition, it is possible to explain the secondary nucleation process. But the stirring and abrasion is not possible to be explained by just monomer incorporation. I had something. I think the starting point is akara. There are 10 to the 5th akara molecule, and here you added the size L crystal of size 40, 300 of them, and P crystal of size 40, 200 of them are added initially. And if the crystal grows up to a size 50, then in order to simulate the abrasion, you divide this size 50 cluster into 2 of the size 25 clusters. So the number increases. But there is no chiral breaking. L and D keeps its almost keeps its number. So no chiral symmetry or no EE enhancement is observed. So only with the monomers, monomer incorporation, we cannot obtain chirality. This process I wanted to extend to incorporate the chiral dimer incorporation to see whether it is possible. But I think it is possible to break the chiral symmetry.
If you break it much longer, what will happen? If you add
This one.
if you add 50 crystals in L, the crystals, the L crystal dominates at last.
No.
Before this slide, please show. Before this slide 13.
No, it's the other way around.
Yeah, slide 13. When you add 100 L crystals are added, whole systems were dominated by L when T equals 2,000. So that is, system is dominated by L by initial 500 and initial 100 accuracy. But in second, next slide. In this case, no, initial fluctuation were added. But in your case, Monte Carlo integrations were done. So during the generation of new crystal, decomposition crystal, maybe there are some fluctuations. But that they didn't increase to the one crystal dominated level by this calculation. But if you increase the time, this system doesn't dominated by one crystal.
No, because the overlapping cannot take place because if the size goes up to 50, it will be split up into 25 clusters. So the merit of large size is lost.
I see.
There's no right.
Different calculations.
Yeah, there are different calculations.
It's
with that reason.
I misunderstood. I thought the calculations are the same and the initial conditions are different.
Different. And the mechanism is different.
I misunderstood. Sorry.
So only with monomer incorporation you cannot get the chiral symmetry breaking. To obtain the symmetry breaking, you have the mechanism to incorporate the chiral unit in your crystal. Then homochirality will be achieved, as Wiedemann's case. That's my feeling.
All right, then. That's well. Thank you. So what did the other think about it?
I made a small presentation.
You know?
Because this might fit in a certain way looking on this problem, not from the point of view of explanation of enantiomers, but we have elaborated a method how to control the crystallization of polymorphs. Polymorphs are crystals which have different energetics. Now, the enantiomers have exactly the same energy, whereas polymorphs have a completely different energetics. And by assuming this mechanism of cluster formation, we can add to the solution an additive which can induce the precipitation of the stable form, stable thermodynamical, the metastable thermodynamical form. And I think that that's something in connection with this, where for the enantiomers we are assuming this to have acti-energetic crystals. But in polymorphs we have even one crystal which is lower in energy as compared to the other crystal, and by some kind of related mechanism which we assume clustering and so on, it is possible to force this particular polymorph to grow. And I think that maybe the mathematics that we have elaborated for these enantiomers may be somehow useful also to explain the process of the crystallization of different polymorphs. Okay.
Yeah, maybe, let's first of all check what the others think. I mean, I see here both Raphael and Jonathan doing calculations while everybody else is speaking.
But actually,
What is your any observations so far?
Very similar to models I've done, but the same thing that purely interacting with the monomers doesn't give you symmetry breaking bifurcation. You need to have interactions between clusters of more general sizes to get symmetry breaking.
Excuse me, are you asking me a question? I don't know.
No, the results are. So I've written down some models that are very similar to yours that similarly don't have a symmetry breaking bifurcation. But if you include dimer interactions, then you can get symmetry breaking bifurcation. So
But that's also what you have, of course, right?
You have the same result.
Well, it's the same kind of model that just maybe if you do not achieve at the end the global the simulation breaking, it's maybe because you remove interesting unnecessary mechanism. And typically, the fact that having this kind of interaction between a chiral crystals and non-chiral seeds, it can augment the non-linearity of the autocatalysis and help. So even in a really closed system, it's what Jonathan had shown, I think, in his last models.
So I've kept cluster dimer interactions of all sorts, whereas you've introduced this 50 particle breaking up into 225s, which is quite a different case, but I'd be interested to see what you finished your work, what your results are.
Because of those 50 breaks up into 25, I have incorporated only the growth step by step, one by one.
Yeah,
and that's it.
Well, I've kept in steps
sufficient.
2 by 2, so
That's
effective
the
diamonds.
working line.
Yeah,
But also, how do you get your models? I mean, you have this model that has hexamers breaking up into 3 dimers, but your model doesn't have a cubic nonlinearity into it. Shouldn't you have some steps in between?
I think that it's the first model was working because you have an high nonlinearity because you have this R6 that gave 3 S2. But in your last model, you only had the breaking was only X15 that gave 2 X25.
Yeah.
Why didn't you have the X60 that gave 3 X20?
Yeah, that's
maybe just the reason because
started to play with. So,
it just really just removes maybe the most interesting reaction.
I can add many.
Which one would be the most interesting? Which one do you say?
It seems to work at the moment that he has this very nonlinear process. That's one molecule gets 3 of the seed.
But that is not the essential part.
Not sure.
Sure.
So, and at the beginning, how do you get your simple systems of 2 ODEs? How do you get your systems of 2 ODEs from a chemical system which has got 6 clusters in it?
I have 2 ODEs is initially there should be this kind of equation.
Yeah.
And I simply put 0 up here.
I see.
You just set all the derivatives to 0 and assume they're all at steady state.
They are already very quickly to the steady state. In any case, what I need is.
Doesn't that give you a more complicated nonlinearity in your equation for the dynamics?
Yeah, but what I really need is to find what is the fixed point of this.
Yeah.
Both was independent of that. That's right.
I only need this equal to 0 situation.
Yes.
And then.
But you draw phase planes which are far from fixed point, don't you?
Yeah, but if the fixed point is racemic, then you will end up in the racemic fixed point. If fixed point is breaks the symmetry, then you are there.
But can you show your phase plane
You can just sketch it maybe, that's good enough.
Some of
You need to.
all the things. And there is a racemic fixed point and
all these other derivatives you've assumed are zero, but they're only actually going to be zero near your fixed points.
This is a fixed point.
Yeah. So near those fixed points, all of those gamma 3 dot, gamma 4 dot will all be zero, or R3 and R4 dot will be zero. As soon as you're away from those fixed points, those derivatives won't be zero.
These derivatives are not zero.
They're not zero.
What is essential is
So-
about the stability of these fixed
Yeah.
points. And for that, this is sufficient
Yeah.
in a sense.
So all you know about your phase plane is the trajectories near the fixed points.
Yeah.
You don't know about them near the origin at all.
For that, you have to.
You have to solve the full system.
To solve
Yeah.
the-
In high in 6 dimensions.
In fact, this is not the fixed point anymore.
Yeah. So your trajectories might not look like that at all.
But what I wanted to
Yeah.
know is the final equals time and that is just close to the fixed point. So I first wanted to know what the fixed point is and what is the stability around this, and that can be observed through this output.
Any more questions? Still not puzzling? Or?
I'm still surprised that if you write down such a big system of equations, and even assuming steady state, you get such a simple equation for the dynamo concentration. It's just quadratic.
Because almost everything cancels out. And what remains is the simple one.
Okay.
That follows your 2005 paper, you say, right? No, does it actually follow you? Is that your 2005 paper or not exactly?
It is written. This equation is written.
Yes.
And if you just assume that these chemical processes are quite fast,
Yeah.
and then put all of them to zero, and then plug that in again, and then you get the
You need to check, of course. Yeah, of course. All right then. Any other comments or questions? Mia is keen on showing us some of his work.
Yeah, I gave a lecture on.
We have a physics colloquium at 3, which means if you just want to show something briefly, for a full lecture that wouldn't be time enough, of course, but...
No, I can show you some questions because I think this is quite relevant.
Then we can do that, yeah.
Okay.
15 minutes, is that now? Yeah?
Okay.
Can you show something in 15
I
minutes?
have a prepared lecture.
No, just show us the essential part that you want to show us.
Okay.
No?
Okay. So, one of our major activities actually in solid state chemistry. And the chirality is just a single problem of that. And one of the questions that we were interested is to understand the process of crystallization from a point of view of stereochemistry. Because of course one can build all kind of models and assume all kind of assumptions of all kind of this, but the question is how really crystal nucleation takes place and how we can explain it on a structural aspect of this part. And our assumption is that we don't know what happened in this region, as you presented, as a monomer, and another monomer, and form all kind of clusters in the system. But what we're saying is that in order for a molecule, for a cluster to cross the critical size, at the moment that it crosses the critical size, it must assume the structure and the morphology of the appropriate crystal. Now, what you might have you can have, let's say, dimers, or you can ask how many molecules I need to have for that particular cluster in order that the cluster can cross the critical size and to give the appropriate crystal. Now, this is a very trivial assumption, and the question is, what is the advantage of such an assumption? And the advantage of such an assumption is that I can use the information which is in the crystal, including morphology and structure that is in the crystal, in order to design auxiliary molecule which I can add into the solution during crystallization, and to see how this additive will affect the growth of the crystal. Professor Saito mentioned the work of Pope, that he put D-glucose inside the solution and then you get one crystal. Why? How the D-glucose actually affects the growth of one of the crystals. This one can really, I think, can be rationalized on terms of stereochemical aspects. But what we are saying here is the following. The solution must be composed of a large variety of clusters. Okay? They are interconverting with one another. They are there. Because if I know that I can get another polymorph from the same molecules, I can organize these molecules in different type of clusters that can give me another product. In the case of the chiral crystals of achiral molecules, we have two enantiomorphous crystals. But if I take a molecule that can give me three... What happens? Okay. But if I take, for example, calcite has three polymorphs. It's calcite, aragonite, vaterite. The same calcium carbonate can form three different crystals. And the question is, what happens in solution? And our assumption is that you have a library of all these possible clusters. And it's a question of thermodynamics now. If one of the crystals is going to grow, then all this system is driven toward the formation and the precipitation of this particular cluster, this particular crystal, and therefore you generate this thermodynamical stable crystal. But now if I assume that I have clusters, because if I have isolated molecules, I cannot operate in this particular direction. But if I have clusters which assume this particular structure, I can add an additive in the solution which can block the formation of this particular polymorph, which can inhibit the formation of this particular polymorph. Because if I have a cluster, if I have a molecule which has to be incorporated in that particular cluster, this cluster cannot cross the critical size. It will prefer to be decomposed back into smaller clusters, and therefore in this way I can ask now myself whether I can give a chance to the second polymorph to grow. Because if I select properly this inhibitor, since I know the structures of the various polymorphs, I can select that inhibitor such that it will interfere with the formation of this, but will not interfere with this particular second polymorph. And therefore we shall see that the entire system will be driven now to a second polymorph, which is thermodynamically less stable as compared to the stable polymorph. And I think this is another advantage, but I think it has many common features with what Professor Saito demonstrated, in the sense that here we have two equi-energetic systems, whereas here I have two systems which are different in energy. And I can draw the entire system toward this particular polymorph, which is even, I think, with the assistance of a very small additive which is present in the solution, and this is done by decomposing the appropriate clusters which are leading to the formation of the stable polymorph. And then now we have even a third system where I can even, let's say, I can even inhibit the growth of the B, and I can get the gamma. Actually, we have done now in the glycine system, we now have the three systems. I can inhibit this one, I can inhibit this one, and I can go to the real metastable phase, which is grown under the same condition, but just adding the correct additive that I can add into the solution. Okay? So this is actually what is our working hypothesis. The structures of embryonic nuclei resemble in structure and morphology to these of the corresponding D3 crystals. This was our problem, and according to that, we can elaborate our system. As I pointed out, you can go to the second one, and then you can get, this is the way how we can control the problem of polymorphism. But you cannot, by this method, by having an additive, to control polymorphism just if you don't assume the composition of clusters. And one of the questions that we were asking ourselves, what must be the size of these clusters? How must be the size of these clusters? Of course, they depend on the structure of the molecule. They depend on the conditions of supersaturation and so on. But we wanted to find one system where we could learn something about the size of these clusters, which could give us some indication where we are standing here. And I think that monomers and dimers and trimers, they are very small species. I think that we have to work with here is much larger clusters, which have to be combined and which can be disintegrated. And we also think that we have examples where if one cluster touches another cluster, this cluster can be reconverted, actually can assume the structure of the major product. And therefore the combination between large clusters is very important in order to explain crystallization in supersaturated solutions. Is there a question, please?
I have a question.
Yeah.
What's the difference between this
Okay, this is a nucleus and this is a crystal.
And
This is a nucleus and this is a crystal.
nucleus means below the critical size.
Yeah.
Below the critical size.
Yeah.
And this crystal means
It's
above
beyond the critical size.
So another new A is should be added to
This one are, let's say, these are either small clusters, NA, which we don't have information about them.
Okay.
But Professor Saito presented in his model. No problem. Here are the nuclei which are at the onset of crystallization.
Okay.
Okay, so they are very close to the crystallization part, and they have the ability to cross the critical size and to form the crystal. So we assume that they have the same structure as the crystal, the same morphology as the crystal, and therefore I shall see immediately how we can use the information of the crystal, of the morphology of the crystal, as well as the structure of the crystal, to introduce a molecule into the solution, which can inhibit the growth of the crystal. We shall learn about how it affects the crystal, and beyond a certain concentration, it can also actually inhibit nucleation whatsoever. But if we select this additive such that it will not interfere with this one, okay, it will give the AB. But if it interferes with this one and with this one, it will give you AY. And in this way, you're generating not two enantiomers, because in the case of enantiomers, all these models of sodium chloride, you say, we have two different equienergetic systems. We have something which is more profound, two differently energetic states, and I can drive the reaction toward this particular, this metastable state by having some kind of additive, which this is my interference in the solution, into the system. And this interference affects all the other clusters here, but not this one. And now this one actually can gain the war, if you like.
So this process is not a crystal growth process, but a nucleation process. Nucleus to crystal is not a crystal growth, but a nucleation process.
We shall see that first of all, in order to test which molecule I would like to use, I'm testing this on the morphology of the crystal. And then if I add a little bit more of this molecule in solution, I know that it affects the nucleus.
So this from nucleus to crystal, more and more, monomer, more smaller clusters should be added to the nucleus.
Or maybe clusters.
Or clusters. So this inhibit kinetically inhibit or thermodynamically inhibit.
I think this is, you see, this is a kinetic process. Because this is a real kinetic process. Because I'm dealing with polymorphs and not dealing with two enantiomorphous phase, when then you have to assume a thermodynamic equilibrium. And they are thermodynamically equienergetics, right? But here I'm dealing with something which is energetically less stable as compared to the first phase. And therefore I can move it all kinetically, everything toward the less stable polymorph. And this, I think, has some kind of analogy done experiments of this when people are using sodium chloride as this model for the crystallization. Should I continue because I've now 5 minutes now. So let me just
informally. Should you? How much do you want him to continue? Because myself will at least go to the colloquium. I should go. What?
The question is if I find it relevant. If you find it relevant to the problem, then I can continue. If not, I can stop.
Yeah, you can maybe make a formal stop first of all, and then you can continue for those who actually don't go to the colloquium.
What's the colloquium about?
High energy. Something.